Hello, Stat 200, and welcome to Lesson 10. This week, you're going to be comparing two groups. You can find this flowchart in your Lesson 10 online notes. This displays all of the different procedures that you should be able to do at the end of this lesson. The procedures with stars next to them here are the ones that your online notes are going to emphasize. All of these procedures can be conducted using Minitab Express, using known distributions such as the normal or z distribution, binomial distribution, or t distribution. These are the ones that are most frequently used in real life. The procedures with the stat key logo next to them are simulation-based procedures. The bootstrapping and randomization procedures are the same for 2 samples as they were for 1 sample in the last 4 weeks. These are the key topics that we're going to cover this week. First, we'll distinguish between independent and paired samples. You'll learn how to construct confidence intervals and conduct hypothesis tests for comparing 2 independent proportions, 2 independent means, and 2 paired means. This week's video is going to be relatively short because I'm not going to walk you through all of these procedures here. There are examples in your online notes, and they follow the same general structure as the confidence intervals and hypothesis tests that you've been performing for the last 4 weeks. Instead, what I want to focus on here is distinguishing between independent and paired samples and selecting the appropriate test. Independent samples come from completely separate groups that are in no way matched or paired with one another. Typically, these are completely different individuals in each group. In contrast, paired samples are related groups where each observation in group A is paired with an observation in group B. Oftentimes, it is the same person or the same object that is being measured twice, once in each group. So, for example, you could measure someone's weight before and after they go on a diet. In this course, you completed the goals assessment at the beginning of the course, and you'll complete it again at the end of the course. So in those examples, it's the same person that is being measured 2 different times. So the measurements are paired by person. It does not always have to be the same person or the same object. They could be paired in a different way. For example, if you're looking at heterosexual couples, you could look at husband and wife pairs. You could also look at mother and son pairs, or pairs of twins. In all of these examples, for every observation in group A, there is a matched or paired observation in group B. Before we go on to selecting the appropriate procedure, let's review confidence intervals and hypothesis testing. When we're constructing a confidence interval, we're estimating an unknown population parameter using an observed sample. Bootstrapping methods may be used to construct a sampling distribution. If certain assumptions are met, then the sampling distribution can be estimated by a z or t distribution. Recall for a proportion, if n times p and n times 1 minus p are both at least 10, then the sampling distribution can be approximated using a z distribution. For a mean, if the sample size is large, so at least 30, or if the population is known to be normally distributed, then the sampling distribution can be estimated by a t distribution. In hypothesis testing, we're determining whether the observed sample likely came from a population with the given parameter. Randomization methods may be used to construct a sampling distribution. If assumptions are met, then the sampling distribution can be estimated by a binomial, z, or t distribution. In Lesson 6, you learned how to construct a bootstrap sampling distribution to find a confidence interval. The methods that we use with 2 samples are the same as those that you used with 1 sample. So here, I use StatKey to construct a bootstrap sampling distribution for p hat 1 minus p hat 2, so the difference between 2 proportions. The 95% confidence interval is the middle 95% of these bootstrap sampling proportion differences. So here, we're 95% confident that the difference between the proportions in the two groups in the population is between 0.120 and 0.180. So it's the same procedure, the same interpretation that you saw 4 lessons ago when you first were introduced to bootstrap sampling. You could also use the standard error method with the bootstrap sampling distribution method, or you could also use this standard error method with a known distribution, such as a z distribution or a t distribution. A confidence interval is always going to be the point estimate, so the difference in proportions or difference in means in the sample, plus or minus the multiplier. This is the value that you would get from your z or t distribution, times the standard error. The calculation of the standard error is going to differ depending on what parameters you're working with. For hypothesis testing, in Lesson 8, you learned how to construct a randomization sampling distribution. So you used randomization methods to construct this sampling distribution to find a p-value. In this particular example, we have a randomization dot plot for the difference in two independent means. So the null hypothesis here is that the means of the two groups are equal, or the difference of the two groups is 0. So the randomization dot plot is centered on 0. When we're working with two independent means or two independent proportions, the null hypothesis is almost always going to be that the two groups are equal. So the center of your randomization dot plot will almost always be 0. The p-value then, we're going to map at the bottom the difference in the sample. So here the difference between x bar 1 and x bar 2 must have been 0.790. This is a diagram for a right-tailed test. So the p-value is the proportion of randomization sample mean differences to the right of 0.790. So we have a p-value of 0.024. So again, this is the same basic procedure that you followed 2 weeks ago when you conducted randomization tests for one mean or one proportion. The difference now is that we're looking at the difference between two means or two proportions. But the procedures that you're going to follow, the interpretation of the p-value is going to be the same. We could also use more traditional methods, so those that use a normal distribution or a t-distribution to conduct a hypothesis test. The general form of the test statistic is always going to be the same. It's going to be the sample statistic minus the hypothesized value divided by the standard error. Here's a quick review of the 5-step hypothesis testing procedure. In step 1, you're going to check assumptions. So this is when you're going to determine which procedure you're going to use, and you're going to ensure that all of the appropriate assumptions have been met. You'll also write your hypotheses. Step 2, you'll calculate appropriate test statistic. If you're using a randomization procedure, this is when you would construct that randomization dot plot. If you're using more traditional methods and you're using either formulas by hand or Minitab Express, this is where you're going to compute the z or the t test statistic. The only exception here is if you are doing a independent proportions test using the Fisher's exact test. Recall from last week, if you're using the binomial procedure, so a Fisher's exact test statistic, you're actually not going to be given a test statistic. Minitab Express will just give you the p-value. So that is the one exception where you won't have anything for step 2. Step 3, determine the p-value. In your randomization dot plot, this will be the area more extreme than your observed sample statistic. In Minitab Express, the p-value will be given to you in the output. Step 4, make a decision. If your p-value is less than or equal to alpha, you reject the null hypothesis. If your p-value is greater than alpha, then you fail to reject the null hypothesis. And step 5, state a real-world conclusion. This is when you go back to your original research question and you say either, yes, I have evidence that there is a difference in the population, or no, there is not sufficient evidence to state that there's a difference in the population. Let's look at a few examples now of selecting the correct procedure. Here's our research question. Are women more likely to diet than men? In a sample of 100 women, 44 were dieting. In a sample of 100 men, 18 were dieting. Let's start by identifying our variables of interest. We have two variables here. One is gender. We're comparing men and women. And the second is dieting. We know whether or not each individual was dieting. So our explanatory variable is gender, and we have two groups, women and men. Our response variable is dieting. This is a categorical variable. Participants either responded yes or no that they were currently dieting. So we have two independent groups, because men and women are totally different samples, with a categorical response variable. This takes us to the top of our flowchart. The question we need to ask now, are n times p and n times 1 minus p both at least 10? So we have to look at both groups, and in both the sample of women and the sample of men, n times p and n times 1 minus p must both be at least 10. So for women, out of 100, 44 were dieting, so n times p equals 44. N times 1 minus p is the number of women who were not dieting. So 100 minus 44, which equals 56. So 44 and 56 are both at least 10. Now we can look at the sample of men. Out of 100, 18 were dieting. So n times p equals 18. N times 1 minus p will be equal to 100 minus 18, which equals 82. So 18 and 82 are both at least 10. This assumption has been met, so we're going to take the top branch of our flowchart. We are going to use the normal approximation method. This is also known as a two independent proportions z-test, and we can do this using Minitab Express. Let's look at another example. Do Stat 200 students tend to score better on the first or second midterm exam? Midterm 1 and 2 scores were collected from a sample of 60 Stat 200 students. First, let's identify our sample and variables. So we only have one sample of students here. We have one set of 60 Stat 200 students. The variables of interest are time, so we want to know if first and second midterm exam scores differ. The response variable, I'm going to say, is exam scores. So we're comparing exam scores from the first midterm to exam scores for the second midterm in one sample. So our data are paired. Every student took the two exams. Our sample size is 60. So we can go on the top branch here, and we're going to conduct a paired means t-test. This is also sometimes known as a dependent means t-test. Here's another example. Are the proportions of Penn State Harrisburg and Penn State Altoona students who are Pennsylvania residents different? So we have two independent groups here. We have our Penn State Harrisburg students and our Penn State Altoona students. In a sample of 20 Penn State Harrisburg students, 16 were Pennsylvania residents. In a sample of 20 Penn State Altoona students, 18 were Pennsylvania residents. So we have two independent groups. Our explanatory variable here is campus, because we're comparing the Harrisburg and Altoona students. Our response variable is Pennsylvania residency. So each student was asked if they're a Pennsylvania resident, yes or no. This is a categorical variable. Next, we need to determine if n times p and n times 1 minus p are all at least 10. For Harrisburg students, 16 out of 20 were Pennsylvania residents. So for Harrisburg students, n times p is 16. N times 1 minus p is 20 minus 16, which is 4. This is not at least 10, so this assumption has not been met. So we're going to go down the lower branch here. We have a research question, so we're doing a hypothesis test. We are going to use the Fisher's exact method. We can do this using Minitab Express. Here's one last example. Do Stat 200 students have higher goals scores than Stat 100 students? So the goals assessment is an assessment that you took the first week of class. I think it was 20 questions that assessed your statistical knowledge and statistical literacy. So it's a quantitative variable. The goals was given to a representative sample of 50 Stat 200 students and 50 Stat 100 students. So here we have two independent groups. We're comparing our Stat 200 students to our Stat 100 students. That is our explanatory variable on the basis of goal scores, which is our quantitative response variable. So we have two independent groups. Next question we need to ask is whether or not both of the samples are at least 30. Both of our samples are 50, so we do have two large samples here. We're going to take the top branch and conduct a independent means t-test. This is the table from the online notes. It should also be in your to-do list for this week. If not, you can ask your instructor for a copy of it. You will probably want to have a copy of this on any notes that you're going to have in front of you for the second midterm exam, and also some version of this on your one page of notes that you can have during the proctored final exam. As always, if you have any questions this week, please post them to the Lesson 10 discussion board on Canvas.